Pokemon Mystery Dungeon is a peculiar series about starting your new life as a Pokemon and exploring these ever-changing labyrinths to prevent the world from ending. Its first entry was released in 2005 for the Game Boy Advance and DS. This has always bothered me. Almost every other handheld spin-off, the trading card game, Pokemon Pinball, Pokemon Puzzle League, Pokemon Picross, almost, and of course the main series, all started on the original Game Boy and Game Boy Color. Because of that, they share this special 8-bit aesthetic and charm between them, and I've always wondered how Pokemon Mystery Dungeon would look in this style as well, if only it was developed a few years earlier. Actually, I've been toying with this idea for years, and now that I've finally learned enough coding skills to execute on it, I decided to find out. And the journey this project took me on was utterly fascinating to me, and I have to explain it. I started by answering some basic questions. First of all, is this type of game even possible on the Game Boy? Well, yes, definitely. This system already hosts 2 other games in an older Mystery Dungeon series called Shiren the Wanderer. Okay, so we could make a ROM hack of this game and just add in some Pokemon and done. But I'm not interested in that. I don't just want Mystery Dungeon on Game Boy, I want the most insane, graphically mind-blowing version possible. I want to preserve as much of the full scale of the original games as I can. Literally, the scale of the graphics is larger than most other RPGs. Just compare the overworld sprites from these games to the ones from the core series. Even the following Pokemon from Generation 4 don't match up. So pulling off graphics like this on the Game Boy is practically unheard of. But of course, it's not as simple as just throwing these assets onto a completely different console, much less a weaker one. Obviously, Game Boy games don't look like this. But why? What exactly are the limitations of this system? That's what we need to find out next. Only once we understand these limits can we push them to their absolute extremes. So, as we start our mission, we'll be uncovering the Game Boy's mechanics, exploits, and breaking points to see just how far we can go. Starting with... Since we're talking about sprites, let's talk about color. On the Game Boy, every pixel is stored using 2 switches called bits, which gives us 4 possible combinations, hence 4 colors. But for sprites, their first color is sacrificed to give them transparency, otherwise everything would be very square-shaped. That leaves only 3 colors to work with, which is not much. But these default limitations defined the look of 8-bit gaming, so it was obviously fine for most things. But for any larger or more colorful sprites, 3 colors is pretty rough. In the case of our Pokemon, it gives up so much detail that it wouldn't even be worth making the game to me. Or at least for the Game Boy Color. The monochrome Game Boy would actually fare better in this department, since you don't have to worry about the right colors, it's just 3 shades of gray. But remember, my goal is to get as close as possible to the original graphics, so thankfully we can do better. One solution is to use 2 different color palettes per sprite, so each of the smaller objects forming it can either use one palette or the other, giving us 6 colors total instead of 3. We'd still have to share some between palettes, usually black, but it's a definite improvement. Better yet though, we can overlap 2 objects to give us all 6 colors in the same place, no duplicates needed. And if we do this for the whole sprite, we can get some pretty great looking results. But we're forgetting something. The object limit. Oh yeah, objects are what most people would call sprites. More specifically, they're the tiny pieces that make up those sprites. Each one is 8 pixels wide and can move independently from the background. They're actually the only other thing the screen can display besides the background, which is just a grid of tiles. So without objects, everything would move like this. The downside is that objects take more time to draw than the background, so the Game Boy can only draw 10 of them per line, which is just half the width of the screen. This is a serious constraint to consider, so let's see how it plays out in practice. Let's say each Pokemon sprite is 3 objects wide on average. I'll deal with the rest of you later. With our overlapping method though, we'd have to use 4 objects or 5 or 6 on just one Pokemon, leaving little to no room for another one. Needless to say, this isn't an option. So we're going with the non-overlapping version to use the minimum number of objects possible. That leaves us with 3 Pokemon per row before hitting the 10 object limit, which is more acceptable, but now we're back down to 3 colors again, leaving our sprites like this. And still, if one more enemy or item shows up on the same line, we're gonna have a problem. This is why old games often have sprite flickering. Instead of dropping extra objects completely, they'll continuously cycle the entire object list in memory, which spreads the dropping out equally between them. So some sprite flickering will be unavoidable during busier moments, but normal gameplay should remain unaffected. But that 10 object limit remains a strict hardware limitation, meaning it can't be overcome through clever coding tricks, so there's no way around this one. But hey, at least we can use 2 separate color palettes on each Pokemon, right? Well, this does technically work, I'll say that. However, it comes with its own set of drawbacks which would be difficult to fully explain at the moment, but as an example, just like there's an object limit, there's a palette limit as well. But we might be revisiting this idea later on. Okay, so to recap, all I want is a way to display more than 3 colors per sprite without using any extra objects or extra palettes, which sadly is impossible. Or is it? Take a look at this sprite, or this one, or this one. They all use 4 colors, except they don't. It's really just 3 colors laid over a black background. And since the 2 are never separated, the illusion is maintained. Many 8-bit games use this 4-color sprite trick, despite their backgrounds looking more primitive as a result. And if we apply this to our Pokemon, we can discard their black outlines and any parts that are dark enough, giving us 1 extra color to work with, and check out the difference. But wait, we can't turn the whole floor of our dungeon into a black void just to pull off this trick. So what if we moved only a part of the background along with our sprites? The problem with this is that background tiles can't move like this. Remember, they're all part of one large grid that scrolls together, and blacking out tiles as the sprites pass over them is too distracting to be worth the added color. So what if we made them smaller? Dividing each tile like this, we could create black squares at twice the resolution. Dividing them again gives us 4 times resolution, and again for 8 times, the same size as 1 pixel. Now, if we gave each sprite its own outline graphics to tell these black squares where to go, we'd have a movable backdrop that covers only the exact area needed by the sprite to use this 4-color trick. I've never heard of this background drawing method used with sprites before, but if it works, it'd finally solve our biggest problem, not to mention the possibilities improving other games. Alright, but there's gotta be a catch too, right? Well, let's just say there are good reasons why games didn't do this. Let's start with the smaller problems and work our way up. For one, we need these black outlines to work seamlessly across the whole screen, which means any color palette used by the background must include this black. Notably, even tiles that don't show black, like this flower, still need to dedicate a slot in their palette to it. This only leaves 3 other colors per tile to work with, which somewhat limits our visual depth. To compensate, I've boosted the contrast of the graphics to start using more black everywhere, which is more in line with other Game Boy games anyway. We can even employ dithering, which is too messy for our Pokemon, but looks just fine on backgrounds. So with some careful planning, we can work around this one. A second hitch has me more concerned, and that's speed. See, we can't actually divide the size of the background tiles and just tell them when to turn black. Instead, we have to fake it by taking each full 8x8 tile and masking out any pixels that would overlap with that section of the outline. This takes time. And on a retro system like the Game Boy, we don't have much of that. Normally, you would just load tile graphics from the cartridge to the system's video memory so they can be displayed on screen. The Game Boy Color even adds a feature that can blast data between these 2 points at 5 times the normal speed or more. Unfortunately, we can't use that. If we want to draw these special outlines to the background, we'll need to manually intercept every background tile in their vicinity and apply the black mask right here before storing them. But wait, if that wasn't slow enough, we also need to shift the outline graphics pixel by pixel to place them exactly under the sprites. Otherwise, they could only move jaggedly like the previous examples. And all of this has to be done using math. Not only for every tile, under every sprite, but on every single frame. But believe it or not, there's a third problem that's even bigger. Let's say that drawing the black outlines took 0 time. Okay, now let's put them into video memory. I'll put this one right here. Oh, that's weird. Let's try here. No? Here? What's going on? If you haven't guessed it, these background tiles aren't fully independent from one another. Rather, many of them are repeated, with the same graphic in memory pointing to multiple squares on the grid at once. This grid is actually another part of video memory called the tile map, and the screen reads from here to draw the background instead of the graphics directly. This has many advantages. Simply enter a tile's number on the map, and it can be reused anywhere with no drawbacks, letting you create entire levels from just a few building blocks. It's memory efficient, easy to update the layout, and doesn't need any new graphics to be copied around once the original is loaded. Retro consoles were designed to be really good at using tile maps like this, and doing it any other way is slower and more complicated. So guess what we're going to do? In order to freely draw our sprite outlines to the background, we must fundamentally change how tile graphics usually work. This means negating any benefits of the map and constructing the entire screen from completely unique graphics, even if that means duplicating the same ones multiple times. But now, changing one tile has no effect on another. Success. This method even solves another issue I haven't mentioned yet. You see, the mapping method is limited by how many tiles you can store in memory at once. On the Game Boy Color, this number is around 500, which is more than enough for most games. But we're porting something from the Game Boy Advance, and the dungeon tiles alone are enough to fill the space almost entirely. And that's before factoring in other assets like the stairs and trap tiles or any status bars and icons. So normally we'd have to make some sacrifices, cutting out the least necessary tiles to fit everything else. But guess what? We don't have to do that here. In fact, we can display a near infinite number of completely unique tiles while also using less memory. Why? Because we're already loading new tiles from the cartridge every frame to merge with the black outlines. That's the whole point of this setup, right? So along with loading the outline tiles, let's throw in any new tiles that would be needed from starting the level or scrolling the screen. And the key is these tiles can come from anywhere on the cartridge. We're essentially expanding the system's video memory from 500 to over 50,000 potential tiles. So how does this take less memory? Because we only need to store enough tiles on the system to cover the size of the screen. And this number is only 400. Are you seeing the potential now? With the combination of extra sprite colors and unrestricted background tiles, we could create something far more graphically advanced than most of the Game Boy's library. There's still more hurdles to clear, but this core concept remains immensely powerful, and I can't wait to try it. So before tackling the speed issue, let's create a simple test program. The goal? To transfer a whole screen of 400 tiles from the cartridge into video memory. Let's do it. So, how do you run this thing? If you haven't done much coding before, don't be intimidated. I'll keep things simpler for now. But I hope I can inspire a deeper appreciation for retro games, because I think this stuff is so cool. If you have coded though, you may have heard of something called assembly. Basically, the assembly language is the most direct way possible to interact with a computer. All other languages must go through a translation. For this reason, it's also the smallest and most efficient, and was the weapon of choice for most 8-bit and 16-bit games. All it does is take the most basic functions a computer can perform, like adding one number to another number, and gives them names, like add. So let's try adding something. The Game Boy turns on, shows the logo, and then starts reading from the cartridge. It's expecting a number. If we put the number 0 on the cartridge, for instance, it will read the 0, then execute function 0 of the CPU. Every number is physically tied to a different function, so when the computer reads one, the circuitry inside it reacts in a way specific to that value, letting all sorts of actions be performed with just a series of numbers. Repeat this process millions of times a second, and you get a basic CPU. Isn't that awesome? I never really grasped what it meant that someone designed a CPU before, but now I get it. They had to literally engineer all the logic of the circuits and any features they wanted the computer to have into basically a giant electronic flowchart. That's incredible to me. Anyway, this explains why a CPU can't just do anything. Each one has its own sort of vocabulary, and writing code for it means speaking that language. Going back to our example, the number 0 in the Game Boy's language does nothing actually, so let's use the one for adding. Now, since the CPU knows we want to add something, the next number on the cartridge is taken as the input. So instead of executing function 1, we add that 1, and there we go. If we keep repeating these two numbers, we'll keep adding 1 forever. But now let's see it in assembly. Ah, much better. Each 198 is now the add instruction, and our 0 from earlier is a no op, meaning no operation. These instructions are much more readable, but are still essentially the same as plain numbers. This is very different from modern coding languages, which are designed to handle the exact details behind the scenes so you can focus on the bigger picture. It's like you're ordering at a restaurant. You can customize what you want, sure, but assembly is like being directly in the kitchen deciding how many grains of salt should go on every morsel of your food. It gives you unparalleled control over every single thing, but that can also be exhausting and more prone to human error. There are more modern ways to code for the Game Boy though, so why not use them? Well, to put it simply, everything will be converted back down to these numbers in the end. And a computer translation from a foreign language will simply never beat out handcrafted code from a native speaker. So for maximum speed and control, we're doing things the difficult way. Right, now that you know what this is, let's see it in action by loading some tiles. I've stored them all in another part of the cartridge, so first let's dox their address to the CPU. It's called a memory address actually, and once specified, we can read and write data to wherever it points. To do this, we use the load instruction to read the data from the address. Then we specify another address to write it to and load the data there. Let's choose the video memory. And bam, we just transferred one tile. Well, not quite. It was actually only 1 byte, aka 8 bits. That's why the Game Boy is called an 8-bit console. It does everything in these units of 8. But we already know that each pixel uses 2 bits, so we'll need 2 bytes to get one row of the tile, and 16 bytes for the full thing. So first we'll start a countdown from 16, then load a byte of tile data between the CPU and the video memory. Then we increment each address to point to the next bytes. To make a loop out of this, there's the jump instruction. Let's first decrement the countdown and check if it's reached 0 yet. If not, we'll jump back up and load the next byte. Let this run, and there, now we've actually copied one tile. But wait, we don't even know which one to copy yet. What we need is a level, or rather a dungeon. In the real games, these are randomly generated using a complex algorithm, but let's save that for later and just use this example I made. It consists of three things: the layout, the tile data, and also the meta tile data. Because a single tile is so small, almost all retro games use larger collections of tiles to construct their graphical chunks. These are called meta tiles. For example, a 2x2 meta tile is just a list of pointers to 4 actual tiles. This is the most common size, but Mystery Dungeons tiles are 3x3, same as the average Pokemon. So not only are we making each block of graphics 9 times bigger, but we're also making the level data 9 times smaller. The downside is these meta tiles mean nothing to the Game Boy on their own. So here's what we do. First, we need a starting position, a camera inside the level layout. This will be the meta tile in the top left corner of the screen. We'll use that meta tile number to look up the list of smaller tiles it represents. One by one, the tile graphics are copied to video memory using our loop from earlier. Only this time, we'll loop that loop to draw them in a square shape. Copy 3 tiles per row, then skip ahead to arrive at the next row. Do that 3 times, and you get all 9 tiles to finish the meta tile. Now we move our camera position to the next meta tile and start the process all over. 3 tiles across, then 3 tiles down. Only this time, we'll loop in a larger square shape to fill the screen. Pretty soon, we have the full 400 tiles, just like we wanted. But here's where the magic happens. Right before writing the tile data to video memory, we can merge it with data from one of our black outlines. Since we're really working with 1s and 0s here, we'll do this with the AND instruction. This is a type of binary logic that will output 1 only if both our tile bit and our outline bit are also 1. Otherwise, it's 0. But 0 is exactly what we want. If we store the outline portion as 0s and leave the rest as 1s, this AND gate will turn off every tile bit that overlaps with the outline, while letting the rest pass through untouched. Pretty cool, right? Let this run, and there, we've printed a custom outline onto the background. These are called bitwise operations and are one of my favorite parts of low-level coding. We'll be doing more tricks with them in the future. Now, to make this test feel more complete, I'll load graphics for the Pokemon itself into memory as well, using the normal method. To make these into objects instead of background tiles, though, we need to leave the tile map and use a different area of the Game Boy called Object Attribute Memory, or OAM. This is the place where objects are created. Each one uses 4 bytes that tell the screen how to draw it: its vertical position, its horizontal position, its tile number in memory, and a set of modifier bits that can do things like flip the object or change its color palette. We can just leave this blank. For the tile number, we'll just increment by 1 with each object to get the next tile. And for its positions, we'll mimic the same 3x3 square shape as the meta tiles, moving 8 pixels to the right 3 times, then 8 pixels down, and starting again from the left. See if you can follow the coding logic for this one too. In any case, these are basically the fundamentals of all retro game consoles and computers in general. And hey, look at that, our 4-color sprites working on the Game Boy. Beyond this point, however, we'll need to implement some more advanced techniques if we want to get here. But I know it's possible, and the problem solving needed to do it will become even more fascinating. Cramming this whole project into just one video would skip over so many interesting things we could explore, so I'd love to make this a series. We still need to add scrolling, enemies, dialogue, and even start brainstorming how this new entry in the Mystery Dungeon series could look and play like. If that sounds like something you'd want to see, or if you have any suggestions for the game itself, please support this video and let me know in the comments. See you next time.